Now we are going to discuss about stability of metal complexes. In stability of metal complexes, why we are going to discuss about stability of metal complexes? Because the complexes will be stable. All the complexes may not be stable. It depends on different factors that we will discuss in further studies. First, let us discuss about stability of metal complexes. For example, if you are considering a system called level systems, what is the meaning of level system? In which the ligands are very active in reaction. If they are replacing very fast, then that is called as labile systems. In such systems, that is labile systems, we will express the metal ligand complex equilibrium in terms of stability constant, because it will move very fast. The ligands will move very fast while forming a complex that are called labile systems. In that type of systems, we will try to express that equilibrium in terms of stability constant. The stability constant we will also call as equilibrium constant. There are two ways to express this equilibrium constant or stability constant. One, stepwise stability constant, and otherwise overall stability constant. What is the meaning of stepwise? If the reaction is happening step to step, A to B, B to C, C to D, etc. If the reaction happening in a one way, and we are taking all together the stability constant, that is called as overall stability constant, we will look at this stepwise stability constant and overall stability constant in the next slides now. Here we can see, just consider an example of complex formation, like metal is going to form a complex with ligand, and here n number of ligands are going to combine with metal to form metal ligand MLN complex. In this one, we are going to consider stepwise stepwise stability constant, right? And let us imagine one metal is going to combine with a ligand, which is forming ML complex, in which let us take the stability constant as it is step 1. It is going to take as K1, that is concentration of product by concentration of product by concentration of reactants. Reactants means metal and ligand, M and N. In this way, we have to write the stability constant. What is the stability constant formula? Stability constant is equal to concentration of products by concentration of reactants. This bracket indicates the meaning of concentration. This bracket indicates the meaning of concentration. Concentration of product by concentration of reactants. How many reactants will combine? If here in this case metal and ligand are combining, so they are reactants, and ML complex is forming, and that is product. In stability constant is equal to concentration of product by concentration of reactants, product of concentration of reactants. That K1 we are taking it. Imagine that ML after forming, once after combining with one ligand, it still react with ligands to form further complex. ML combining with one ligand and producing Ml2. In this case, K2 is equal to the similar way product Ml2 divided by Ml into concentration of Ml into concentration of L. The same formula. Concentration of product by concentration of reactant into concentration of other reactant. Here the reactant 1 is here, reactant 2 is here. In the same way, let us assume Ml3 is forming from Ml2 upon reaction with ML ligand. Then that case ML2, that is here ML2, here ML3 it is. It is not ML2, it is ML3. ML3 is going to form by ML2 and ligand. So here we can see, here it is not K2, it is K3. K3 is equal to ML3, that is product concentration, divided by reactant is which one? ML2 into concentration of ligand. So this is K3. In this way, we can make many stability constants for stepwise formation. Now let us see for the nth ligand. Nth ligand means n minus 1 ligands. If it's reacting with one more ligand, it will produce mn ligands. Where equilibrium constant or stability, overall stability, no, stepwise stability constant is Kn. that is equal to mln divided by mln minus 1 into concentration of L. It's just like concentration of product by product of concentration of reactants. Here, very important thing is what is this N? This N represents the maximum number of ligands that is attaching to the metal. That is coordination number or number of ligands, right? That is coordinating with the metal. And now here K1, K2, K3 all are what? Stepwise constants for this stepwise stability constant for this particular complex formation. And here we are looking a very important point is what is the relation between the stepwise constants? Stepwise constant is particular steps. If you are comparing, right, this K1 will be always greater than or equal to K2, K3, and K3 is greater than or equal to Kn, something like that upon till the Kn. Why? What is the reason behind this? Why K1 is more compared to K2? Obviously, the reason is very easy to understand because the ligand is already bonded to a metal, right? For example, one metal is bonded to one ligand. When this ligand is already bonded, the incoming ligand, right? The incoming ligand repels with the already existing ligand. That is the case, the K2 will be less than K1 because the ligand already bonded to the metal ion repels the incoming ligand. For example, if you are taking this M and L ligand, the incoming, this is L1, this is L2. This L2 will be repelled by L1 and hence K2 will be less than K1. The same way, let us assume metal plus Ml plus one more ligand. Obviously, what will form? Ml2 will form. What happens? This Ml ligand, already M is coded with a ligand. This Ml ligand will not allow this ligand to enter. That time this K2 will become less than K1. The same way, what will form here? Ml2. The incoming K ligand, that is L3. If you're imagining labeling as a third ligand as L3, just for identification, we are labeling here. It will form as ML3. So what happens? Again, here there are two ligands. We can see here ligand and ligand. These two ligands will repel the entry ligand. The ligand which is entering here, right? That ligand will be repelled by the ligands which are present in the metal, right? So here Kn will be less than K1. So here this Ml1, Ml and L interactions will discuss in detail here. For example, Ml ligand already formed. One more ligand is going to enter. What will happen? This ligand will have some electrons, right? That electrons will be repelled by the electrons of the ligand which already present with the metal. Because of this one, the K2, because the stability constant here is K2. K2 will be less than K1 because K1 occurs fast because there is no ligand repulsions concept in the first case, that is with K1. In this case, only one ligand is repelling with other ligand. If you're considering again with Ml2 here, one more ligand, imagine one more ligand is going to enter here. What happens? This ligand will experience two type of experience repulsions from two ligands, right? And so obviously, while forming Mn3, that is stability constant K3, again K3 will be less than. So it will be same throughout this process till it is forming MLN. If you are keep on moving towards the formation of MNL ligand, the stability constant will be less and less and less. So Kn will be less than the previous one, like that. It will continue till the end, right? And moving on to the point called overall stability constant. Before moving to overall stability constant, I hope this point is very clear. This Kn will be less only because of the already existing ligand and the entering ligand repulsions. Between them, there is a repulsions. That's the reason the Kn will decrease. And moving on, this is overall we discussed in this one stability constant, stepwise stability constant. And moving on to overall stability constant or cumulative stability constant. Cumulative stability constant we will indicate with beta 1, beta 2, beta 3, etc. Here we are just considering, not considering stepwise, we are considering at a time. All the ligands, n ligands are forming mRNA complex, right? And in this one, we are just taking the overall stability constant. In this one, we are overall stability constant. Again, the stability constant formula is almost same only. Concentration of product by concentration of reactants. Here, just overall stability constants we are going to indicate with beta 1, beta 2, beta 3, etc. Right? Here, beta n. It's the same case, same way. Just like the stepwise stability constant, here also overall stability concept is same. Here, the formula is mln divided by concentration of L, m into concentration of L whole power n. Now here, beta 1, beta 2, beta 3, beta n are what? They are overall stability constants or cumulative stability constants. They are overall stability constants or cumulative stability constants. Now there will be a relation between this overall stability constant and cumulative stability constant. Stepwise stability constant and cumulative stability constant. Between them, there will be existing a relation that we are going to get from this particular equation. So here, let us consider this expression for beta 3, cumulative stability constant. What is the formula? ml3 divided by concentration of m into concentration of n. If you are seeing here, right, what is the difference between beta 3 versus K3? Let me tell you about that one very clearly. If you are looking into the previous case, right, in previous case, the ligand is combining with metal once after other ligand. That means M combining with L forming Ml. This Ml again combining with one more L forming Ml2. Again one more L, Ml3, something like that. This is stepwise. Stepwise we are considering, right? Only metal is free at one first step. From next step onwards, metal is combined with other ligands. But in this case, it's not like that. You can see here, every step metal is free. Every step metal is free. And so here, compared to here, the clarity should be there. And one more thing, here ml ml is the obviously product concentration by reactant concentration where we are writing, it will be individual. Here in this case, we can see ligand power will come. In the previous case, it's not like that. It's not like that. Why? Because the ligands are individual. Here the ligands are coming as cumulative. At a time, all ligands, either one ligand or two ligands or three ligands. Whatever it maybe, they are coming at a time. Now we can see here ML3, that is ML3, we are considering for beta 3, right? ML3, concentration of M into how many ligands will combine? For beta 3, it will combine 3 ligands. So ML3 divided by concentration of M into concentration of L power 3. Now let us get the relation between this beta 3 with the stability constants. That's stepwise stability constant. This is overall stability constant, right? We are going to get the relation between this stepwise stability constant and overall stability constant. To get that, we have to do small things here. That is multiply this one, ml3 divided by concentration of m into concentration of L power 3. Just multiply with ml and ml2. And obviously, if you are multiplying again, denominator also divide with ml and ml2. What is going to happen? Here is going to happen is like this. This is beta 3, right? ml3 divided by m into L power 3. What we are going to multiply? Concentration of ml, concentration of ml. Concentration of ml2, concentration of ml2. As we are multiplying and dividing with same, it will be same only, right? Now, let's separate the same thing in a expand the same thing actually. Now, this is ml and divided by concentration of m into concentration of m. This is ml2, you can see here, ml2 is here, and concentration of ml, concentration of m. Next, ml3 is here, ml3, concentration of ml2, concentration of m. So, what is happening here? In this case, if you are considering this one, right, concentration of product by concentration of reactant into other reactant, that is K1. Because these are there in the stepwise stability constant. This particular concept exactly, this is matching with the K1. This is matching with K2. This is matching with K3. So this K1, K2, K3, if you are writing here, this product K1, K2, K3 is exactly matching with the overall stability constant beta 3. That means there is a relation between overall stability constant and stepwise stability constant. If you are taking beta 1, it will be equal to K1. If you are taking beta 2, it will be equal to K1 into K2. Same way, beta 3, it will be K1, K2, K3. So, if you are moving on, right, the overall stability constant is a product of all together. If you're taking n type n beta, then it will be K1, K2, K3, K4, 7 up to n. In this way, we can relate the overall stability constant, and this is overall stability constant. Overall stability constant. And this is stepwise stability constant. So this is the relation between overall stability constant and stepwise stability constant. The relation between them is very clear. Beta n is equal to from n1 to n sigma 1 to n k1. So overall stability constant and stepwise stability constants are related in this way. Let's expand this equation to further. If you are taking logarithm on both sides, log beta n, that is overall stability constant, is equal to sum of the logarithms of all the stepwise constants, stepwise stability constants. So log beta is also used to measure the stability of the complex. Here, obviously, it will be helping to find out the stability of the complex. Now, how the stability of complex is can be determined based on these factors? Very easy. Larger the value of stability constant. Of course, it is a stepwise or overall. In general, larger the value of stability constant, the reaction proceeds to the formation of product. The reaction proceeds to the formation of product. Larger the value of stability constant indicates that equilibrium lies towards the right hand side. That is towards the product, towards the formation of complex. So, which is going to favor the formation of complex? More is a stability constant. More stability constant favors the formation of complex. More stability constant. If stability constant value is more, then it will tend to it will help to form complex easily, right? In general, a complex is said to be stable if log beta, that is overall stability constant, is greater than 8. In general, stability constant should be greater than 8. That is logarithm log beta greater than 8, then the complex is going to be stable. So here we have discussed about stability constant, that is stepwise stability constant and overall stability constant.